Hi everyone, my name is Daniel Voskergian from Alcott University,
Oh, wait,
and
hold
today
on.
I'm going to present you
Is Daniel available? Nope. Okay. Here we go.
a research abstract entitled Predicting Diabetes Complications from Electronic Health Records Using Machine Learning Algorithms. This work is done in collaboration with Prof. Borjo Bakir from Abdul Gol University and Prof. Malik Youssef from Zifat Academic College. In this presentation, we are going to give a brief introduction, the study objectives, the utilized datasets, the proposed methodology, finally the experimental results with some conclusion and future work. As a brief introduction, diabetes mellitus, commonly known as diabetes, is a chronic metabolic disease characterized by insufficient insulin production by the pancreas or ineffective utilization of the insulin produced by the body. Diabetes nowadays poses a critical global health concern, significantly affecting millions worldwide and leading to substantial morbidity, disability, and mortality rates, especially in low and middle income countries. In this aspect, increased glucose levels beyond the average level in the bloodstream may affect various major human organs over time. This can result in long-term life-threatening health complications. The most prevalent types of complications in diabetes are classified into microvascular and macrovascular disorders. Microvascular disorders impact small blood vessels and include conditions such as nephropathy, neuropathy, and retinopathy. On the other hand, macrovascular disorders damage large blood vessels and encompass peripheral vascular disease, cerebrovascular disease, and ischemic heart disease. Early detection of diabetes related complications usually poses a significant challenge, as symptoms often manifest only in later stages. Therefore, regular medical checkups and routine screening are crucial for patients with diabetes. However, what if we could predict these health consequences before the need for doing such tests? This could definitely alleviate the healthcare burden of diabetes, improve care pathways, and enhance targeted and specialized preventive measures, consequently preventing or slowing down their onset and development. Hence, assisting clinicians in predicting patients at high risk of developing diabetes related adverse consequences is very crucial nowadays. Nowadays, hospitals and healthcare providers widely adopt and deploy electronic health record systems. Similar to paper records, EHR store various forms of information about a patient during a hospital visit, including hospitalization details and patient-specific medical data, such as medical history, laboratory tests, vital signs, diagnosis, and prescribed medications, in addition to other informations. Utilizing patient-specific data recorded in EHR with data mining and machine learning algorithms can contribute enormously to biomedical and clinical research. It allows the analysis of complex interplay between various extracted features from those EHR datasets, which enable researchers to delve deeper into diseases, understand their progress, uncover hidden patterns and correlations, initiate interventions, and devise preventive mechanisms. However, the wealth of EHR data is not always freely and easily accessible to the research community. The main reason is that they often contain sensitive or regulated patient medical data, which impedes their optimal utilization. To overcome these obstacles, a promising alternative is to use realistic synthetic data generated by deep generative models such as generative adversarial networks and variational autoencoders. Synthetic data, being artificially created, can replicate the attributes of actual data without having a direct correlation, which means there is no one-to-one relationship to the original patient's records, making them resistant to re-identification. So, what is the main aim of this study? The main goal of this study is to utilize synthetic clinical health records that track the diagnosis trajectories of diabetes patients and employ a novel approach to feature engineering, utilizing XGBoost feature selection combined with various supervised machine learning algorithms to develop predictive models for four main complications of diabetes mellitus, including retinopathy, chronic kidney disease, ischemic heart disease, and amputations. Regarding the utilized data sets in this study, we have used two main EHR data sets. Each contains pathologies for nearly 1 million synthetic patients, created using the dual adversarial autoencoder technique and were sourced from a real cohort in the health population database within the Andalusian health system in Spain. The main difference between the first generation and the second generation dataset is that the first one was developed for CAMDA 2023 challenge and has an age range labels categorized by decades. However, in the second generation dataset, it was developed for CAMDA 2024 and it has an enhanced age resolution where each visit labeled by specific years rather than decades. The original EHR dataset is structured in the following format, where each record includes an organized list of visits for each patient. An exception is made for the first visit, which contains the gender label. However, subsequent visits are accompanied by an age code label, along with a corresponding list of chronic diseases, one or more pathology codes that co-occur during that visit. Regarding the age code, it is represented in dataset 1 by an age range for decades and in dataset 2 by specific years. For dataset 2, to reduce features number generated by our feature engineering approach and to ensure consistency with dataset 1, we have transformed the age resolutions from years to decades. To this end, each dataset now contains 10 age range labels, 83 ICD-9 codes, and 2 gender values. This slide illustrates a snapshot of the raw data in the EHR dataset. As we can see here, the datasets exhibit several issues that necessitate several pre-processing steps crucial for training a machine learning algorithm. In this aspect, we have conducted several tasks to transform the dataset into a two-class format. These tasks are visualized in this figure. First of all, we have performed the following record cleaning process, which involved removing empty records, records with no gender value, record with both gender value, records with gender value only, there is no registered visits, and records without diabetes code. All the patients included in this study are diagnosed with diabetes. Then we iterated through each column, each representing one visit, to perform the following pre-processing tasks. We replaced empty visits or visits that contain an age range label only with no pathology codes with null values as we can see here. In some visits, the age range appear between or after the ICD-9 codes. To ensure consistency among visits, we reordered them by placing the age range label first. Thereafter, we split the original data structure, which included the age range label and multiple diagnosis codes, into individual pairs. Each pair now consists of the age range label paired with one of the diagnostic codes. Finally, we ordered the pairs within one visit in an ascending order according to the diagnostic codes. Subsequently, we iterated through each record performing the following additional tasks. First of all, only the first appearance of each diagnosis was kept, as they are chronic diseases. Secondly, we eliminated null visits from the sequence and reassigned the subsequent visits to their correct order, as we can see here. Thirdly, if a record contains a null age range label in one of its visits, We handled missing values by selecting the next available age range value to fill the gap. If the missing age range appeared in the last visit, we used the previous age range label to fill the gap. If all visits were missing the age range label, the entire record was deleted. Fourthly, we removed individual records from the analysis who were diagnosed with the required endpoints, developed a complication before being diagnosed with diabetes. Fifthly, the visits that occurred before the diagnosis of diabetes also were excluded. The reason for point 4 and 5 is to ensure that our analysis focuses on predicting the development of complications, specifically in patients with ongoing diabetes. By excluding data that precedes the diabetes diagnosis, we aim to train our models on information that is more relevant to the progression and management of diabetes related complications, thereby improving the accuracy and effectiveness of our predictions. To this end, the given dataset represents a multi-label classification task, where each record may be associated with multiple endpoints of interest. A patient may have multiple complications at the same time. In this study, we will tackle this task using a series of binary classification approaches. To create a binary class dataset for each endpoint, we first extract the required endpoint from the EHR record to serve as the positive class label for the classification task. In order to avoid data leakage, all visits starting from the hospital visit in which patients were diagnosed with the complication that we are predicting were excluded. Records that do not have the required endpoint are labeled as a negative class instances, with the last visit are excluded to maintain a consistent prediction of complication-free, no endpoint scenario. It's important here to note that we retain records that include at least one hospital visit after the diagnosis of diabetes and before the occurrence of a diabetes-related complication. To this end, the generated datasets were unbalanced with fewer positive class records than negative ones. To address this issue, the class were balanced by randomly selecting the same number of negative class records as positive ones. At the end of this stage, we had four balanced datasets extracted from each main dataset, one for each of the four complications. At the feature extraction phase, for each dataset, we generated a unique K features by identifying distinct combinations of age range labels and pathology codes within the dataset. Gender was also added to this final list. Afterward, we converted each EHR into a K plus 2 dimensional representation vector. In order to preserve the sequential order of visits, we carefully assigned each element in the patient record a value that corresponds to the order of the hospital visits in which they occurred. Finally, we applied normalization to the final features using the min-max formula. After experimenting with various feature selection algorithms, this study is carried out using the XGBoost algorithm since it performed the best in our case. In this context, the top 25, 50, 100, 150, and 200 features were used to train various classification models. In this study, we chose decision trees, random forest, XGBoost, AdaBoost, and LogitBoost. This table summarizes the performance metrics of the final models tailored to each complication trained and tested using dataset 1. As we can notice here, we achieved an accuracy between 69 and 75% and an AUC between 75 and 84%. Regarding dataset 2, we achieved an accuracy between 72 and 75 and an AUC between 79 and 84%. As per literature, an AUC greater than 75% signifies clearly useful discrimination performance. Among others, XGBoost and Random Forest demonstrated the best overall prediction performance. This observation underscores the importance of employing tree-based ensemble algorithms for such problems. One plausible explanation could be that XGBoost and Random Forest leverage an ensemble approach, combining multiple models to address the shortcomings of individual models. This ensemble helps in reducing variance and enhancing prediction accuracy by aggregating the strengths of different models. In our study, we employed XGBoost feature selection to examine the impact of reducing the number of features used during the training process. As observed in the following figures, all endpoints except the last one demonstrated a steady improvement in AUC from 25 till 200 features. Beyond this point, the performance remained relatively stable. However, for the last endpoint in dataset 1, it peaked at 150 features and began to decrease after that. Similar observations can be noticed in dataset 2. Finally, when comparing our feature engineering approach with the traditional bag of features, where each ICD-9 code, gender, and age range label is considered as a separate feature, and their occurrences are used to build the record feature matrix, significant differences emerge. Although the conventional bag of feature approach yields fewer distinct features, less than 100, our results presented for dataset 1 and 2 respectively demonstrated the superiority of our approach. For instance, instead of getting 77% for endpoint 910, we can gain 84% using our novel feature engineering approach. Instead of getting 73% for 1401 endpoint, we can gain 77% using our approach. For dataset 2, we can also attain similar results. For instance, we can get an AUC of 81% for the 910 endpoint rather than getting 73% using the bag of feature approach. Also, we can get an 84% AUC using our approach for the 703 endpoint rather than getting 72% using the bag of feature approach. Our method not only performs better when training the model on all features, but also excels when training on a subset size similar to the conventional approach. As a conclusion, this study developed prediction models for diabetes complications using novel feature engineering, feature selection, and machine learning algorithms. Although this study achieved good results, external validation studies are necessary before considering their clinical implementation. Thank you so much for listening and hope to see you next year in CAMDA conference.